Uh, Hello, I'm Yang Keao, an intern developer at PinCap. Several months ago, we implemented time skew chaos in Chaos Mesh. This is a very cool feature. Nowadays, some distributed systems are highly dependent on monotonically increasing timestamps. So time skew injection could find or cause deeply hidden problems. In a simpler situation, the implementation is quite straightforward. I believe everyone here knows how to set the system clock. But in the cloud environment, we need to set clock for only one process without affecting others, which turns to be a very difficult problem. Well, you may ask, as we have used namespace such as network namespace to inject chaos in for only one process, is there something like a namespace for time? Unfortunately not. Time namespace is only available for kernel version greater or equal than 5.6 and only supports a few clock IDs. So before Linux 5.6, all processes in Linux share the same clock. There are not any provided ways to do this chaos. We have to look for or explore a new way to do this. It may be not elegant, not simple, but it's very twisty and fascinating. In this talk, I will introduce the roadmap of the implementation of TimeSkew. Kubernetes and operator-related concepts will be ignored so that we can focus on how to inject the TimeSkew for a single process. A straightforward inspiration is that we must understand how the process gets time. If we understand the routine, we may find bottleneck to inject our chaos. Here I have listed several different methods. First, you could use system call directly with syscall instruction and 228 syscall number. Oh, I bet that most of you don't write assembly language and don't use syscall instruction directly in 21st century. Second, you can call clock at time function in vDSO, which we will talk about it later. Or mostly, I think you will use functions in the standard libraries for every language runtime, such as instant now in Rust or time.now in Go. This is a very common, doesn't it? You can also use external services to get timestamps, such as TrueTime API, which is used by Google in Spanner. After we have investigated the implementation of time-related functions in every different programming languages, we can conclude that clock at time vDSO call covers most situations. But vDSO, we have talked about it several times, which may have confused you. What is vDSO? I will introduce it right now. What is vDSO? It's a mechanism to run some functions provided by the kernel in the user space. It contains several different functions, one of which is clock at time, which we use to get time mostly. It doesn't like other dynamic libraries which are loaded by LD.so. The vDSO is allocated and loaded by the kernel when a process starts. If you read the maps file of a process, you can find this part of memory here. All these functions are organized in a standard ELF format for the convenience to link and parse. As we have mentioned above, if we can inject clock at time vDSO call, somehow modify the return result, we can inject time skew for most applications. Yes, again, just like what we have done, let's analyze the normal call routine of vDSO. I believe the whole coroutine cannot be that safe or solid, so we can find weak points to create chaos. Let me list the whole coroutine of calling a function in vDSO. First, you can find the start address of vDSO in procfs AUXV file. See here, as you can see, the first line is two 64-bit integer. The first one is 0. Oh, the first one is 2, 1, which means the second one is the start address of vDSO. But actually, you can read and parse the maps file in procfs, which will give you the same result as above. After parsing this part of memory according to ELF format, you can find the start address of clock get time function, then simply use call instruction to call it. All these steps are done automatically in language runtime or libraries now. And finally, the procedural in vDSO clock get time function will run and returns. As you might have noticed, the running process and clock get time function are both in user space. All the binary codes are in the target process memory space, which means if we can modify the binary codes of clock get time function, we can do anything when a process call clock get time. The ignorant process runs the first step, the second step, the third step, the fourth step, and finally call into the part of memory which can be modified by you. The binary codes are anything for a CPU. It's under your command now. You can even ask it to exit or to kill itself. But that's not what we want. What we want is to simply return a modified time. Now the implementation of TimeChaos is right in front of you. We can make it jump to a prepared fake function at the beginning of clock get time, which will return the modified time. So we can split the implementation into three smaller questions. One is how to modify the memory in the target process. The second is how to implement the fake function. The third, how to load a slice of binary into the target process memory. For the first question, we will introduce ptrace. You may don't know ptrace, but as a developer, you must have used it. Most functions of GDB, such as setting breakpoints, watching, and modifying variables, running expressions, they are all implemented with the help of ptrace. In ChaosMesh, we will also use ptrace actually. Ptrace poke data to write bytes to a specific location in target process memory. Then we have to decide the content to write. As we have said, it's a simple jump instruction. Jump-related instructions are quite simple. We can set the RAX register with the target address and then jump to it. The left part is the instructions and the right part is the corresponding binaries. You can compile it with the instruction manual and your smart brain. The red lines are the target address, which is a 64-bit integer. Now we have solved the first question. After calling the clock get time, the process will jump to the prepared function. Then let's solve the second question, how to implement the fake clock get time function. The main problem is how to get time because the real clock get time has been modified by us. But we have listed several different ways to get time, this will not bother us. Recall the first method to get the time mentioned before. Mentioned here, we can use clock get time syscall. Then we can modify it according to these static variables. The logic is shown here as C programming language. Then we can compile it with GCC and modify some small parts, resulting in the corresponding binary slice of the fake function in the right part. After the fake function has been prepared, the only question is left. How to load this fake function into the target process memory and get the target address of the jump. First, we need to allocate memory. How? Yes, the mmap syscall will help. We will use ptrace to run the mmap system call in target process. Let's see how it can be done. We could write 0f05 at our IP address, which means syscall instruction. Then we should modify registers, modify RAX to 9, which means mmap, RDI to 0, which means the first argument of the mmap is null, and RSI, RDX, R10, R8, R9 are the following mmap arguments. Then we use ptrace single step to run this instruction and stop. At this time, the mmap function call the mmap system call will be run by the target process, and the return value will be stored at RAX register. Finally, to avoid breaking the target process, don't forget to back up and restore the modified register and memories. After we have allocated memory in target process, we can write the fake function binaries to it now. At this time, we use another syscall called process VM write v rather than ptrace because it's faster and more stable. You may want to know why we don't use process VM write v to modify vDSO. Recall that we use ptrace poke data to modify vDSO to make it jump to a fake function. That's because vDSO part of memory is read-only privilege, and process VM write v requires the target memory part is writable, but ptrace poke data doesn't require it. Okay, we have solved all these small problems, and the roadmap to implement a time skew is clear now. Let's recall and conclude them. First, load the fake function into the target process and get the start address of fake function. Second, use ptrace to modify variables in the fake function according to the user requirement. Third, use ptrace to modify vDSO's clock@time function to jump to a fake function when the target process calls it. Okay, that's all I have for today. At the time and presentation form limit, you may be still not very clear about the detail of the implementation. I believe the best way to understand it is to use chaos match chaos and read the source code, which is not very long actually.